Crash course in the cosmic microwave background. So, I've told cosmology classes before, if I ask a question and you don't know the answer, just stick your hand up and say cosmic microwave background. Because it's the most likely thing to be the answer to whatever question I've asked. And I'll just be happy that you think that's the answer. So here's a crash course. So take a photo of the whole night sky in optical that looks something like that. Take a photo of the whole night sky. I think this is in H1, and it looks like that, obviously dominated by, so in optical, obviously dominated by stars, blocked out by dust clouds. In radio, in H1, dominated by the galaxy. In gas, and you can see the small and large Magellanic clouds there, and some sort of, streams over the top and all that sort of stuff. There's one particular wavelength where if you take out the emission from our galaxy and look at the night sky at about 1 millimeter, you get that, which looks like noise, kind of is. This is the cosmic microwave background. Look at the whole sky in about 1 millimeter wavelength, where you can take out the emission from the galactic plane, which would be here, obviously. And what you find is the temperature here, which you can measure, is almost perfectly uniform across the whole night sky. So these changes between red and blue here are 1 part in 100,000. So what's going on? The other thing that's interesting is if you measure the spectrum of that light, you get, as we did with the FIRAS instrument on the Kobe satellite in 1994, you get the data points here. And the line going through all those data points, amazing data, because this is actually error bars times 400. That's 400 sigma. So just astoundingly good data. And the line that's going through those is a 1 parameter fit with an equation that was written down by this guy in 1900. Oh, now I'm going to work it out. When did Planck? Might be 1898. Might be 1905. No, that's too late. Around then, about 100 years before this, Max Planck wrote down that equation. What he was thinking about was if you had light and matter and they were perfectly in equilibrium with each other at the same temperature, so the matter's not heating up the light's not heating up the matter, what would the spectrum of light be that you get out of that? Black body radiation. So you do some sort of calculations. It's the sort of really the first quantum mechanical result. Because if you just assume that light's a classical electromagnetic field, that calculation doesn't work. If you assume light, actually no, it was simpler than that. He didn't even assume that light comes in packets. If you assume that the walls of the container, the matter, only absorbs at certain wavelengths in certain packets, then you get this equation. And the only thing you need to put in is the temperature. So Planck got there 100 years before Kobe. That, if you ever had to do an experiment in a lab where you had to create a black body and then measure its spectrum, and if your results looked like this, we would kick you out for fabricating your results, because there's no black body we've ever seen on Earth which is that good. The number there is 2.725 Kelvin, right? 2 degrees above absolute zero. Right, so there's light in the sky. It's coming from all directions. It's at the same temperature to 1 part in 100,000, and it has the signature of light and matter perfectly coupled at 2.725 Kelvin. And so far as we know, as best as we know, there is no such matter out there today. You would have to fill the universe with something almost perfectly at that temperature and have nothing heat it up. Like, it can't be a blend of 2.725 and 2.8 and 2.6. It has to be exactly at that temperature and just be radiating. And there's nothing around like that today. The best sort of idea of what that thing might be involved an idea that was floated by Fred Hoyle, that maybe there are iron needles that just throughout the universe all perfectly radiating at exactly that temperature. How you fill the universe with iron needles is something he never quite answered. So, what this almost certainly indicates is that in the past the universe was hotter and denser. So it's a relic radiation. You can't make it today, unless you can think of a way of filling the universe with light matter exactly in equilibrium with the light around it at 2.725 Kelvin. But in the past, the universe, if it was hotter and denser, you could have those conditions, and this light had just left over from then and has cooled off. So, getting a little bit more into details. The sort of epochs in the history of the universe. 20 minutes after the Big Bang, a lot has happened. Big Bang nucleosynthesis has basically been and gone. The universe is 74% hydrogen, 25% helium by mass, and 1% a bunch of other stuff. And what's important is out of all of that, there's a baryon to photon ratio. Basically, for every particle, every proton, say, in the universe, there are about 1 billion photons. So if you turn that number upside down, it's 6 times more. So matter is just incredibly outnumbered in the universe. But there's this, proportion of the elements, and obviously enough electrons around to have the universe be neutral, and it just expands and cools. At this point, the temperature is probably something with 8 digits in it, 10 to the 7, 10 to the 8 Kelvin. I should probably work that out anyway. So things are way too hot for any neutral atoms to form. But all that's happening now is the universe is cooling off. There's 3 important things that happen next, over the next sort of 100,000 years. In the very early universe, there is more energy in the light, in the radiation, in the things moving at the speed of light, so that includes neutrinos as well, actually. There's more energy in that than there is in just ordinary matter, like in protons, neutrons, electrons. But they are changing at different rates. Expand the universe by a certain amount. All the photons are still there, all the particles are still there, but all the photons have also been, you can think of them as all being stretched as well. So as well as the density of photons going down and the density of particles going down, because you put them in a bit of a bigger box, the universe is expanding, all the photons lost another factor of their energy because they're all got redshifted. What that means is, at some point, matter's going to take over. One of them's going down like the size of the universe to the 4th power, and the other one's going down to the 3rd power. Matter's going down to the 3rd power, right? Particles. And so at some point, matter's going to take over. We call that era matter radiation equality. Also, the universe is cooling off to the point that at some point, if an electron goes around, say, a proton, falls into an orbit, the universe is cool enough that it doesn't get immediately kicked out of that orbit. That's what we call recombination. It is a terrible name because it should just be combination. It's not recombining neutral atoms. There never was a time before then when there were neutral atoms. Right? Recombination. The photons are cool enough that most of the electrons are part of atoms, not part of just floating around in empty space. Right? Not free. A related idea is decoupling. So imagine you're a photon and you've got 1 billion friends before you find an electron out there and you're bouncing around the universe, right? This is just a bounce. Electron plus photon is electron plus photon, right? You just bounce them off each other. How long until that process basically becomes inefficient and the typical photon in the cosmic microwave background doesn't hit anything ever again? When the universe is young, hot, dense, bouncing off all the time, that time scale is very short. As it expands, eventually you get a point where the photon there's so little matter around, there's so many of these photons, they just don't hit anything for the rest of the history of the universe. That's what we call decoupling. It's a freeze-out process, which I'll explain a bit more in a second. And keep another time. Right, matter radiation equality, we can go into these equations if you really want. There's a different way that they scale the size of the universe cubed versus the size of the universe to the 4th power, do the maths. This point where the amount of energy in matter versus the amount of energy in radiation, protons, neutrons, electrons, dark energy, is about a redshift of 3,200. Which is a really big redshift if you're used to galaxies, but a really, 100,000 years ish after the Big Bang. When that happens, there's a change in the relationship between the rate at which the universe expands and the temperature of the universe. Never mind these equations, that's all you sort of need to know. We can track all of these things. Recombination. So the universe is cooling off. Recombination, remember, is when is the typical electron attached to a proton? Now, that doesn't happen exactly when the temperature drops below how much energy it takes to knock the electron off. So here's a proton, here's an electron, ground state. How much energy does it take to kick that electron completely free? The answer is 13.6 electron volts. When the temperature of the universe, which is just the energy per particle, hits that limit, a typical photon can't knock off an electron. But because they're not all at the same temperature, the tail, the high end of the distribution, the occasional really energetic photon can still ionize things. So actually it doesn't happen at that temperature, it happens at a lower temperature of 0.3 electron volts. But the number you need there is a redshift of about 1,300. That's the point at which the universe is more neutral than ionized. The thing that is well named is reionization, which happens because of stars way later on. Right, that last thing, decoupling. Remember, higher redshift is earlier time, so we start here and go this way. While ever two processes have sort of interacting very quickly, they can reach an equilibrium. If they don't reach an equilibrium, you get frozen in wherever you just left equilibrium because things stop changing. If you assume equilibrium, then the ionization state of the universe does this, it just drops off the cliff, right? 1 is all the electrons are free and 0 is all the electrons are in atoms, and it falls off like this. However, because the universe is expanding, it doesn't stay in equilibrium, and so it sort of drops off in a slightly different way. But there's decoupling. The average photon in the universe doesn't hit anything on those sorts of timescales. So, again, we can do a nice calculation to work when that comes out, and it's roughly about the same time as combination, a redshift of about 1,000. We all know that. What's happening there is crucial to what we see in the night sky. Whenever you see anything, you see the last thing that the light scattered off. Right? That 3 there, you see, because the last thing the light hit before it entered your eye is this. If I put a fog in this room, put it on my smoke machine to make it cooler, right, and there's a whole bunch of fog here, the light leaves here and then bounces off some other stuff. So you don't see it. Right? Whenever you see anything, you see the last thing it scattered off. So what did the light in the cosmic microwave background last scatter off? It last scattered off an electron when the universe was about 300,000 years old. Close to 400,000 to be honest. This is called the last scattering surface. You're looking at this board, this is the last scattering surface. If you think about a star, it's a gas, there's not really a surface, but there is a last scattering surface. Where was the light I see from the sun? Don't look at the sun. That's that whole, what do my eyes hurt? The last thing you see in the sun is basically at what point is a photon bouncing around the sun? When would it last hit something in the sun and take off into the universe? That's the surface of the sun, the last scattering surface. One way to think about the cosmic microwave background is it's an inside-out star. The hot plasma is out there and we're inside of it, right? Because of the difference in time, it's the past of the universe. But that's the last thing you see. What you're seeing is some photon, some electron out there, 400,000 years really, 380,000 years after the Big Bang. That's what you're seeing. So the picture of this sort of inside-out star is here we are at the center. There's a redshift out there back in time, a long way away, of a redshift of about 1,000 where the light last scattered, although it's not a perfectly quick process, so that the size of that region is about 80 in redshift. What's nice is because the expansion of the universe affects, this is the black body function. Anyone not seen this equation before? Tis a doozy. That's the function that Planck, basically the function that Planck derived. Right? Because So H, fundamental constant, K, fundamental constant, the frequency, the temperature, because those are affected the same way by the expansion of the universe, this shape of the function doesn't get distorted, it just moves to as if it was a lower temperature. That's why it still looks like a black body today, which is nice. Good. I won't go too much into this. Cosmic microwave background discovered in the 1960s. That is a microwave receiver in New Jersey somewhere. Basically, these two individuals, Wilson and Francis, were trying to, they just made a very, very good microwave receiver. And they pointed it at the sky and found that no matter what they did, where they pointed it, there was this hum, this hiss. Those are audible things. There's noise in the receiver no matter where they pointed it. And if you had an old school TV, it picks up the cosmic microwave background as well. You just can't convince yourself that you've seen it because there's noise and things. If you have a really, really good receiver, you can convince yourself that your noise level should be here if there's nothing, but it's up here. So I really am receiving something that looks like noise from the universe. It's funny, the theorists got there about the same time down the road in Princeton, which is also in New Jersey, were trying to, Robert Dickey and his group were trying to build a version of this. This wasn't as good as the Bell Lab, about the same time, the early 60s. So this was the real, we've seen a relic of the night sky.
Sorry, so where does this, so you said that this was in the 60s?
Yes, 65.
Where does this fit in with the radio astronomy groups in Australia and that sort of thing? Is this, this is probably going to be more of a Ray question.
Yeah, so this is a much higher frequency in the
Yeah.
radio.
But that's still all the same principles, right? Just at a high frequency?
That's right, yeah. So radio astronomy in the 60s was alive and well in Australia, people using the lower frequencies. So here they're using the high frequencies. They're actually driven by interference. They're using these frequencies for telephone calls. And so they're being plagued by this hiss on the telephone calls. They're trying to find out what's causing it. We haven't mentioned pigeon droppings either.
No, yeah. One of the, like, we've got some problem with our receiver. What's going on? Well, some pigeons have roosted in it. Let's go clean up the pigeon droppings. And that didn't solve the problem. It was either the pigeons or the start of the universe. Those are the two hypotheses. And it's a great example of, you know, if you do your job well enough, you've got to get rid of all the boring stuff before the interesting hypothesis becomes the one you can actually include. I won't go into this too much. Someone could have scooped them in the 50s, I think, late 50s. There was someone studying particular energy bands in a carbon and something else molecule, cyanogen, I think. Basically, you look at a molecule out there in space, and for some reason, it's as if it's bathed in this temperature of about a couple of degrees because one of its lines is being excited more than it probably should be if it's just hanging out in empty space. But, you know, whether that's a real temperature, we don't really know. It's all that particular paper was willing to say. Okay, the real fun starts when we look at the anisotropies. In other words, the differences. They're only 1 part in 100,000, but there's a lot of information in there. What could make one part of the cosmic microwave background a little bit hotter or a little bit cooler than other bits? Well, one is if we're moving through the sort of rest frame of the universe, there's a Doppler shift, right? So you know, there's a radiation field. If I go hurtling that way in some, you know, some direction at some fraction of the speed of light, the light coming at me seems to be hotter, and the light, if I look behind me, seems to be a bit cooler. So this is a Doppler shift which creates a dipole, you know, there's one particular direction. There's the formula. We can work that out. We are in fact moving through the cosmic microwave background's rest frame at about 371 kilometers a second. So what the cosmic microwave background actually looks like is this. If you project it onto a flat surface, obviously, there's one direction in the sky where it's brighter and another direction where it's, sorry, not brighter, hotter and slightly cooler by about one factor of 1 in 1,000. If you then remove that dipole and remove the galaxy, that's when you get back to this image. All right, so what does the rest of it? Well, as well as we're moving, like, so if we went back in time to find that last electron at the scattering surface that the light, that the light bounced off, what, if that electron's coming towards us, that's gonna change things to the same idea, Doppler shift, anything coming towards us is gonna seem a bit hotter. If that electron is in a gravitational well, if it's in an over density of the universe, then light redshifts as it gets out of gravitational wells. So for light, you shine a torch upwards out of the earth, it redshifts on the way up. So there's that. There's also what would create a gravitational well is there being an over density of matter at a certain point, but then there's probably an over density of light there as well. So if that electron is just hanging out with other electrons, then there'll be an overdensity there as well, never mind the mass. There's a relationship between an overdensity in the number of photons and and a sort of increase or decrease in the temperature. These effects together, those last 3 and 4, are both related to there being an inhomogeneity over there. The electron that we see is just in a denser bit of the universe. Those two actually compete with each other for the sort of perturbations, the overdensities we think there are in our universe. Gravitational redshift wins. So overdensities are cold spots. If I see a bit of the universe, a bit of the night sky in the cosmic microwave background, which is a bit colder than average, those two effects tell me it's probably an overdensity, the light's redshift. There's stuff that happens along the way. If along the way it finds some other electrons that it wants to hang out with, like in a cluster, that will affect it. That's called the Sunyaev-Zeldovich effect. So here's the sort of light coming across the universe. If it goes into just a static galaxy without touching anything, it'll get blue shifted on the way in, red shifted on the way out. That's fine. If, however, the galaxy is growing, then it got blue shifted into a sort of shallower well than the red shifted had to then climb out of. And so there's that effect called the Rees-Schaumer effect. Martin Rees down Schaumer. Oh, just to trace Albany, supervisor me, Martin Hainault, Martin Rees, his supervisor Dennis Schaumer.
Oh, that's my great-great-granddad's.
The one up before that is Dirac, so it's
Oh,
all happening there. Good.
That's pretty cool.
Yeah, it's there. Photon diffusion. So again, because it is a statistical, stochastic, chancy process, there's that electron over there, and it emits, the light bounces off it, but it's not all perfectly coupled together. The universe is changing. So there's a bit of fuzziness out there as well, especially on small scales. So all of those come together for this. So how do we actually analyze this? Well, let me first illustrate a Fourier series. Hopefully you're aware of this. If you put, this is a sine wave illustrated with going around a circle. If you put the right combination of sine waves together, represented by circles on circles at different wavelengths, you can basically make any repeating pattern that you want to make. This is Fourier theory, and if you're doing any radio astronomy, you really need to understand Fourier theory. So if I just go ahead, this one's really nice. If you put why did we go backwards? Hang on, in the middle here somewhere. Yeah. So if you do lots and lots and lots and lots and lots of circles, you can make this as the sawtooth wave. Right? And Fourier theory will tell you how to do all this properly. Now, your ears are doing Fourier transforms on sound. So you're not analyzing the sound that I'm producing in terms of, where each peak is of everything. You're analyzing in terms of frequencies, right? So, lower or higher, right? So this is basically saying if you want to, make a certain noise, you need a mix of the basses and the tenors and the altos and the sopranos and all that sort of stuff. But if we're looking at the cosmic microwave background, we need to think about what patterns, not just wiggles in one dimension, but wiggles in multiple dimensions, 2 dimensions on the surface of a sphere. And this is giving Albany flashbacks of what we're trying to make her do. So the equivalent of, there's not just one way to wiggle, right? There's sort of different patterns of how to wiggle on the surface of a sphere. Here's a way of demonstrating this. suppose I ask you to do a map of the Earth. I'll give you a sphere, but then I only give you a paintbrush with a paintbrush head is like this big, right? Then you can sort of like, there's Europe, there's Russia, right, and there's Australia down the bottom. The finer the paintbrush I give you, the more you can start to fill in the details. So that's what this double sum down at the bottom here is doing. As you get smaller and smaller brushes on the surface of the sphere, you can fill in more details about the surface of the Earth. Reverse engineering this, you find out what these terms are. So how much of the big brush do I want to use when painting Earth, and how much of the little brushes do I need when I paint Earth? We can do that with the cosmic microwave background, and what you get is this rough shape. So this is, I'll show you this in more detail later. These are basically, here are the large scales and here are the small scales. What does it look like if I contribute those to the night sky? The answer is, as you go to smaller scales, you can see the sort of noise gets smaller and smaller. What's crucial about these is that they depend on how much stuff you've got in the universe. So, for example, as you put more baryons, more ordinary matter into the universe, the different wiggles start to change. That's something we can modify. It works for all the other cosmic parameters as well, which gives you the final glorious data. This is from either WMAP or Planck, or there must be Planck. So there's those numbers, multipole moments. There's an equivalent angular scale of, you know, how big compared to the Earth is the paintbrush that I give you. How do you paint the cosmic microwave background so you get all the scales and wiggles right? You need to have this distribution of paintbrushes. And so this one basically tells you how much baryons there are once you get back to the physics. And this one, basically the best evidence we have for dark energy from cosmology, not just from galaxies. So here's the thing. So for example, the fact that things got fuzzy on small scales is the fact that this dies off. So these are the very small scales where photons and electrons just sort of mix together because it's not a perfectly coupled process. But here's that. There are, what's amazing is that the sort of standard cosmology with 6 free parameters is that line, which is doing a really pretty marvelous job of going through those data points, and a real challenge for anything that doesn't go through those. So you do all of that, you do your fitting, and you get back to what's the universe made of, and you have some lovely table of all the numbers. How much baryons are there in the universe? How much dark energy, basically, dark matter, sorry, is in the universe? A bunch of other things. There's that value of H naught that's actually in tension with the local universe one, but there it is, and there's a whole bunch of other wonderful numbers. Age of the universe, 13.8 billion years, all that sort of stuff.
Sorry, are each of these parameters one of those multipole moments, or is that?
No, these will all affect, actually, this is the one to do. So each of those parameters is a way to change this shape. We'll change this shape in a different way. And so, for example, you know, basically the height of that peak there, you can see is related to the baryon. Now there's some degeneracies, there's other processes that affect the peak. But, you know, you can imagine just moving the peak up and down until it lies right on the data, and that's telling you the baryon density of the universe, baryon fraction of the universe. This is why the cosmic microwave background is just the answer, right? In your microwave, it just gives us a whole bunch of numbers about the universe that can be derived in other ways. We can double check all that sort of stuff, but it gives us a lot of them very nicely. So that is the cosmic microwave background. There, 2 o'clock, right up.
There you go.
Questions? These are people's careers, right? So I've given you half an hour. Don't worry if you don't understand the details. The physics, especially of how, of what you need to do to understand why this happens, for example, is quite involved. But ultimately, it's sort of heat and light and a bit of gravity and yada yada yada.
Why millimeter?
That's it. So there's a relationship between the temperature and the wavelength at which a light, so there's a temperature between there's a relationship between the temperature of the hot thing and the wavelength at which it peaks at. So the Y millimeter is because it's 2.725 Kelvin. Why is it 2.725 Kelvin is a really interesting question because it changes with time. Wait a billion years, it'll be lower. If we'd appeared a billion years earlier, it would be different. So the answer, the question of why is the cosmic microwave temperature that 2.725 Kelvin has to be related to when are observers likely to turn up and measure cosmic microwave background, which obviously is a much messier question because now people are in it. But we have to be because that's the question you're asking. Why are we alive at this particular epoch when that's the temperature?
So what frequency would it be if we weren't redshifted to X? What would the frequency this would have been observed at the Big Bang?
Oh, so
Because I mean, this is millimeter because it's redshifted to whatever cosmic micro,
Right.
1300 instead of 1300, I think you said. If this was rest frame, what frequency would that be?
so so you can turn each of these epochs. What do I put it? So, for example, decoupling, which is basically the time. Go out there and find the electron that last bounced off the photon you just saw in the cosmic microwave backlight. Get in your time machine, go back, find that photon, find that electron. Sorry. If it's 2.725 today, Kelvin, it basically goes up proportional to that number 1 plus Z. Redshift like that. So throw 1,000 on that. It's 2,000-ish Kelvin. 2,700, 1.1, 2,800, about 3,000 Kelvin. So that electron was 3,000, 3,000 Kelvin degree plasma when light last bounced off it and then it came to us. Which is, order, the surface of the sun's 5,800. So it's, factor of 2, the sort of about equal for a cosmologist. It's that sort of plasma that we're dealing with. And then as you go back in time, it just gets hotter and hotter and hotter. We don't see that for the same reason you can't see behind the screen, because this is the last thing the light scatters on.
So another way of answering the question, if we're observing at 3 millimeters now, at a redshift of 1,000, we'd be observing at 3 millimeters divided by 1,000, which is 3 microns. So near infrared. So if you're sitting there at the Raman's decoupling, you'd use a mid-infrared telescope instead. But can I add something else?
Please.
Is that right? So it's quite interesting that a few millimeters away is the optimum wavelength. That's where it peaks. But clearly you can actually observe it anywhere down the black body curve. People do, because we want to see, is that actually a black body? And so even at 20 centimeters, they're completely messed up by all the radio sources in the sky. But people try subtracting those off, see whether you can still detect the CMB. The answer is yes, you can. At very low frequencies, also as you go to very high frequencies, you can see it. But actually, even with the Planck data at a few millimeters, they still have to subtract off the radio sources. And that's a problem because we don't actually know the spectrum of most radio sources very well. So we extrapolate from our 1.4 gigahertz measurements using minus 0.8 or something. And that's actually not a very good predictor. So there's lots of work on this as well.
That slide your mouse is on now, Luke, the 1 part in 1,000 temperature variation, is that, when we're talking about the CMB, is that a what?
That's the average.
Yeah.
Right? So
Because 1 part in 1,000 seems to me like, who cares?
100,000.
1 part in 100 is like, who cares? But
Yes.
we obviously care because it's different colours.
Basically perfectly smooth.
Yeah. So what's crucial is, big or small, the point is information. When we can work stuff out about why this pattern. It would have looked different if the universe had been different. So we can learn some stuff about our universe if we understand the physics that made this. Because the thing
Crazy.
is, like astronomy, anything you understand in enough detail, you can start to tell about something else, right? So you could, the cosmic microwave background, as I said, is there in your TV, but you don't understand all the other sources of noise. So you can't, it does detect it, but you can't detect, you can't work out whether it's really there just by pointing your TV at the sky or whatever. Right? You have to be Wilson and Penzias and build a really good instrument and clean off the pigeon poo. And then what's left is the thing you're after. So the point is that, you know, yes, it's small, but if you've accounted for everything else, what's left in here is the universe. You can work some stuff out.
We used to get silhouettes of planes. You remember the old days of the old AM antennas, and you'd be watching TV and we'd get silhouettes of planes as they'd fly over, coming across the screen. It was cool. Just reflecting.
Good. Any,
I have a question. So how CMB is a proof of the Big Bang Theory?
wow, proof is too strong. I think the best case is just, you know, there's definitely a black body out there, right? And black bodies don't have, you know, it's such a particular shape of the curve. It's very unlikely that a bunch of stuff in the universe just happen to be, you know, producing exactly that right shape. So there's something out there that it's coming from every direction in the sky. Right? And in particular, if you're worried a lot about the galaxy, the thing you can do is look through the galaxy and then out of the galaxy, and then at least check that makes a bit of sense. It has the same temperature to 1 part, to 5 decimal places. And it has this signature, right? This Planck worked this out 100 years ago. Get that perfect equilibrium coupling between matter and radiation at 2.725 Kelvin. But then you just think, okay, what astrophysical environment in the universe today could work it out so that all of its parts were spread almost perfectly across the night sky, and all of it was at the same temperature to 5 decimal places, like 2.725 Kelvin. Right? The surface of the sun can just about do it, be at the same temperature. But because it's really hot and really dense, so there's time for the light to bounce and the electrons and the light to get to the same temperature, and then it comes to us. So, but that's at 5,800 Kelvin, where that'll happen quickly. These light bounces really, really slowly and efficiently off, at 2.725 Kelvin, off anything out there in the universe at those temperatures. Because it's not ionized, there's no electrons floating. But you're messed up in all sorts of low energy physics of, helium would be like, it's just really, really low temperature stuff. So how would you fill that out in the universe? Well, if you think that that's impossible, that there's just nothing out there filling the universe, which we haven't seen except for this, then it's got to be a relic. It's just left over from an earlier time. And it would more likely be a relic if the past was hotter and denser. And that's a lot of a way towards, it looks like a Big Bang. Again, the challenge is my other book. Find a better explanation if you don't think the Big Bang is a good explanation.
I add something to that.
Please.
So I'd actually turn it the other way around. So if you remember Fred steady state theory, for example, that would predict 0. If you go out there with Planck and measure the temperature should come out to 0. So most theories of cosmology, if you don't have a Big Bang, you predict that empty space will have 0 temperature. But Robert Dicke, before this was measured, had calculated if there were a Big Bang, would you see any remnant warmth? And he predicted that you should see about 2.7 K. So having predicted this model of the Big Bang, then these guys they didn't even know about Dicke's paper. They went down and they say, hey, we've got a problem like this here. Oh shit, we're measuring 2.7 K. What could be doing that? Is it pigeon droppings? Meanwhile, down the road, Dicke had predicted exactly that number. So that was really if you predict something and somebody measures it, that's pretty good confirmation.
Cool. Speaking of that sort of line of thinking, 60 years between black body predicting 2.75 and it being measured, or that shape, sorry.
Yeah. There's still one free parameter.
Yep. Are there any other theories that are currently around that you think might take 60 years to actually be able to measure?
There's a neutrino background as well. So cosmology's predicted since quite early on that there's a last time that neutrinos interact with anything around, and their energy density will be roughly the same as the energy density that exists here. The problem is your TV can pick up that. It's nothing. Yeah, if we could make something that observed the neutrino background, the cosmic neutrino background. Amazing, but yeah, we just don't have the technology.
Neutrinos we get 6 a year or whatever it is.
Sorry?
Neutrinos we get 6 a year or whatever it
Yeah,
is.
it's, and they're higher energies that are easier to detect, so. It's a really, really lovely prediction that's in every cosmology textbook, and I can take you through it. You end up with a lovely factor of it's like 11/4 to the power of something, and that's the temperature of the two of them. And then you go, we have no idea whether that's correct, but it was really nice physics. Part of it was for this one, it's not entirely, and so that number does depend on, as I said, it was different in the past, different today. So around about 2, 3 is as much prediction as you can make, unless you know when you're going to observe the universe, you don't really know ahead of time. But the idea being structure can't form when the universe is just a plasma, and especially when radiation is dominant, how much time are you going to need after that to make anything interesting like a galaxy or a star? And that gives you then, if decoupling happens at a couple of thousand degrees and it takes you, the universe has got to expand by a factor of a couple of thousand, then you'll get a couple of kelvins of cosmic microwave background. Good. All right. There you go. Thank you very much.
Thank you.
We're all see Aaron.